Hi, Mat220 Calculus 1. So we're going to start our lesson in calculus, but this is kind of just a basic review of a lot of algebra concepts. We're going to talk about section R1 first and kind of review some of the basic concepts in here. And one of them is graphing, okay? So we've done graphing. We're going to try to do graphing by using substituting in numbers and replacing the variables with numbers. So in other words, we're going to make a table. So one thing I like to do, let's try to solve this problem, which is fairly easy. If there are no powers involved in the problem, we know this is going to be a linear equation, which means it's basically going to be a straight line. And so we're going to substitute in values of x. This is your independent variable. And this will give you answers for y, which is dependent on what values we put in for x. So if the equation is written y equals, we always want to replace variables in the expression part of the equation, not in this part of it, but in the expression part. Okay, so we're going to just substitute in some numbers for x. And you can use negative numbers or positive numbers. I'm just going to make it simple on myself and just use the numbers 0, 1, and 2. And then we'll see what y values we determine from that. So if we put in a 2, this is kind of a workspace. I get 2 times 0, 0, plus 1, 1. So when I replace x with a 0, I get a 1. Okay, now I'm going to replace x with a 1. So this is 2 times 1. I should maybe put this in the parentheses to show you the x is being replaced with these variables, 2 plus 1, 3. Pretty basic. And now I'm going to replace the x with a 2, 2 times 2, 4 plus 1, 5. And then I'm going to try to graph this. This axis, of course, is the x. This is the y. We're going to go 5 direction. Let's just put a few numbers up here. And of course, if we had a fancier graph, it would be nice. But so if x is 0, y is 1. If x is 1, y is 3. And if x is 2, y is 5. Okay, so pretty simple because this was a linear equation. All the points should fall in a straight line. All right, let's try one that's a little tougher though. What if we have this one? Y equals x squared minus 1. Now here we have a variable with an exponent. So this means it's going to be this is a quadratic one, which means it's probably going to be a parabola, but it's going to be a kind of a curve. Okay, we're going to deal with a curve. So we're going to, again, substitute in values for x and y. But on this one, we usually like to put in some negative values, kind of see what's happening. And let's take a look. So we're going to put in some negative values in here. Let's put in, let's start off with a negative 2, and then we'll go to a negative 1, a 0, a 1, and a 2. So this way we have a number of variables. Variables for x. We have a lot of numbers to put in place. Here I only use 3 because I knew it was going to be a straight line. Here it's going to be kind of a curve, and I don't know exactly what's going to happen. I have a pretty good idea. What we are going to do in calculus is work on these quite a bit. And we're going to use rules of calculus called derivatives to help us try to solve these problems and make it a little bit easier. So you might think it's a little bit easier. We're going to substitute a negative 2 for the x, and that'll give us negative 2 squared is 4, take away 1 is 3. Now, if there's a number in front of this, like 2x squared, you're going to substitute for the x squared, then you're going to multiply it by the 2 if there's a number in front. Let's change this problem to 2x squared minus 1 so you can see. So this is going to be negative 2 squared, which is 4, times 2 is 8. Minus 1 will now give us 7. Okay, so it's kind of important that if you have a number in front, don't multiply these together because that would give you negative 4 squared, negative 16. You make a big mistake. Okay, so we're going to keep the 2 in front. This is a negative 1 squared, which is 1, times 2 is 2, minus 1 is 1. Okay, put a 0 in here. You can't go wrong on that, can you? 0 squared is 0, times 2 is still 0, minus 1 is a negative 1. Okay, we're going to put in a 1. 2 times 1 squared is 1, times 2 is 2, minus 1 is 1. And if I put a 2 in here, let's see what happens. I put a 2 in here. I get 2 squared, which is 4, times 2 is 8, minus 1 is 7. So square, multiply, subtract. All right, so you can kind of see this is going to be our turning point right here because you notice these numbers are the same. So that's kind of telling us that it's symmetrical to probably the y-axis here. So let's take a look. Here's x, here's y. At negative 2, we're way up here at 7. Let's go up a little bit higher, 7. And at negative 1, I'm all way down here at 1. At 0, I'm down here at negative 1. At 1, I'm back up at 1. And finally at 2, I'm way up here at 7 again. So you can see it's a very symmetrical type graph. If you compare this one to the one in the book, you notice that because this had an x squared, I put a 2x squared. You notice that mine is skinnier. And that's what's going to happen. If you put a coefficient in front of here, it becomes more narrow, the graph. The opening is more narrow. So, and if you put a fraction in there, it becomes wider. All right, let's try another one here. X equals y squared. Well, notice that this problem is written kind of backwards. We could try to rewrite it, but I'm going to try to graph it the way it's written. Now, where a lot of students go wrong on this is because they're so used to substituting for x, they're going to put 0 and 2 or something like that. You want to substitute for the y and then figure out what the x is going to be. So we can't put in very huge numbers. Let's start with a negative 3. So I'm putting in values because, see, this is your independent variable, and we're trying to find a dependent. So I'm going to put in a negative 3, and so x is negative 3 squared, which is 9. Now I'm going to put in a negative 2 for the y value. Negative 2 squared is going to give me a 4. This way we don't have to, I mean, it would be hard to kind of pick these numbers for x. So we want to substitute, this is an inverse function, so we want to substitute for the y instead of the x. And sometimes it's a little confusing when you're not used to it. Negative 1 squared, I'm putting in a negative 1 squared, 1, 1. Putting in a 0, x equals 0 squared, which is 0. Putting in a 1, x equals 1 squared, which is 1. Putting in a 2, x equals 2 squared, 4. Putting in a 3, x equals 3 squared, 9. All right, so let's see what happens here. 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 1, 2, 3. Okay, so when x equals 9, way over here, y is negative 3 down here. Oh, I can't even see that. It's so far away. Okay, When x equals 4, y is negative 2. When x is 1, y is negative 1. Still down here. When x is 0, y is also 0. But something strange happens here. When x is 1, y is 1. So this is kind of weird. When x is 4, y is 2. Well, usually when we're graphing x, we only have one distinct answer, but here we have 2 points. So when x is 9, y is not only negative 3, it's positive 3. Now, if we connect the dots, we see it's a parabola, but it's been turned on its side. Rather than this way, it went this way. Okay, and the reason this is so hard for us sometimes to visualize is because this is not a function. This is a function. A function is when we can draw a straight line through this graph only one time. But if we draw a straight line, a vertical line through this, it's going to go through it twice. That's what means it's not a function. And that's why it's a little bit harder for us to graph it, because we're so used to, like, this is a function. This is a function. But when we try to graph a non-function, they're usually a little bit harder to graph because we don't really visualize them so much. Now, one thing I want to point out is there's some quick checks in the book. If you can't do too many problems, and you should try to do as many as you can, especially later on when we do derivatives, but you can always try these quick checks and see if you can do those problems. On a problem like this, where the variables are on both sides, you want to rewrite this. Bring over the x to the other side, and then divide. Of course, this would still be plus 10. And then divide everything by negative 5. Now, if you remember the shortcut for graphing, and we want to kind of eliminate as many negative signs as we can, then you could use that. If you don't, and you're making a table of values, because 5 is in the denominator, you want to use multiples of 5. Like I went in this problem, if I only wanted 3 points, I would use negative 5, 0, and 5 for x. And then I get a nice one graphing. So, all right. So this might be a opportunity for you to recall some of these problems. And then the answers to those quick checks are in the back of this section, I believe. Okay, we got some more to do on this one. Besides graphing, we want to look at something else. We're going to do a lot of graphing later on. So we just want to get a kind of a quick look. We're going to look at page 9 here, and we have a theorem, theorem 2 we're going to look at. It's a little variation on theorem 1. This is an I, or we could call it an R, over N, T. So what do these things mean? Well, this is to find compound interest, or it's used for compounding things, how fast things are growing, like the virus and stuff. We can use how fast it's growing, the rate of growth. It's compounded, so it's growing much faster. When we have a compound function instead of a simple function would grow like this. Compound function grows exponentially. See, this has exponents, so it's going to grow much. Starts out slow, but then it grows very fast. If you notice the virus, what's happening with the virus right now? It's accelerating. We see 1 out of every 4 people tested are showing signs of having the virus. So it's growing very rapidly. Okay, so let me tell you, this is to find the total amount at the end. This is the principal, or how much we start out with. We usually refer to that as the principal amount. the starting amount, how much we're going to start out. If it's money, we're maybe starting out with $1,000, and we're going to put it in a bank and see how fast we can get it up to either a certain amount or see how much it grows in a certain amount of years. 1 is just part of the formula. This is the number 1. I is the interest rate, like 6%, but we have to change that interest rate to a decimal. So we're going to move our decimal point over 2 places. So we're going to write that in decimal form. That's where a lot of students get messed up. They put a 6 there. N is the number of times it's compounded. So if something is compounded 1 time, once a year, it would be 1. If it's compounded every 6 months, then that's 2. If it's compounded quarterly, that's 4. Monthly would be 12, and so on. So N is the number of compounds. And this N and this N are the same. And then T, when we put compound, and T is the number of years. Now, different formulas might have different letters. They might put an R here. They might put a Y here for years, so it kind of depends. So we're going to do one. This guy put $1,000 in the bank. That's your principal amount. And they invested in this fund. So he put $1,000, let's give him an extra 0 there. And it was invested at 5%. So 1 plus not 5, but 0.05, 5%. And it was compounded quarterly. Quarterly means 4 times. 4 times a year, every 3 months. The money is compounded. It means it grows. You're getting interest upon interest upon interest. N is the number of times it was compounded, 4. And T is the number of years. And he wants to find out at the end of 3 years how much money he's going to have. He isn't doing anything. He's just letting it in the bank. Now, what I advise on a problem like this is you multiply the 4 times the 3. If you put it in this way into your calculator and you don't put this in the parentheses, which you should have, then it's going to give you the wrong answer every time. So I advise that you probably just multiply. They're usually pretty small numbers. Multiply them together, you get your answer. 12. Let's see if this is anything important. Can't find a phone. Let's see. No. I don't know. More messages that I don't have time to answer. Okay, so let's just put this into the calculator the way it's written. Grab yourself a good scientific calculator. Clear this out. We got 1,000 parentheses 1 plus 0.05, not 5, 0.05 divided by 4, just the way it was written, parentheses. And we're going to raise that, you raise 0 to the 12th power. And say that's why I think it's a little bit easier. I mean, 4 times 3, how hard could that be? And this will give you the amount of money. We're going to carry it out to the nearest penny, and we're going to round it up if this number is a 5. If it's not, we're going to keep it the same. So it looks like 1,160.75. And so by just keeping his money in the bank and not doing anything to it, he gained $160. And he let the bank do the work for him. And this is how people get rich. They just let the money do the work. All right. So that's an idea how you're going to do R1. It was kind of a quick review of R1. We're going to look a little bit here at R2. It's meaning by the bank. R2. By the way, I want to show something else on this graph. Let's say the graph started exactly at this point and this point. We're going to do 2 things. We're going to talk about a domain and a range. The domain means how wide is this graph. This is going to go, if it has an exact beginning, exact end, it's going to go on this axis from 3 to -3. That's the domain. We usually start with the small number, then to the big number, left to right. The range is how tall is this graph. The height, the lowest point it goes down to for the y on the y-axis is 0, and then it goes all the way up to 9. That's the range. So when we talk about domain, we're talking about the x's. The x's go. And these have actually exact beginnings, so we put them in brackets instead of parentheses. So that's the range and the domain. Let's try another one. Let's see if I can get one here. That other one. Okay. Well, let's turn this one on the side, just for the heck of it. So if this graph was going this way, this was up here at 7, the domain would go from -1, I put D, it's going to go from -1 all the way, let's say these were our endpoints, to 7. If we were talking about going down this road right here, went from -1 to 7. The range goes from this point, the low point right here of -2, to the high point of +2. And that would be the range if the graph was turned this way. Okay, so we'll talk a little bit more about that. Okay, we're going to skip over a couple of things, and we're going to look at a problem like this. We're going to look at a little function notation. Instead of saying y equals, say, x squared, we can say function of x equals x squared. These two things mean exactly the same. Why? But we use function of x because it has advantages. Like if I want x to be a -3, I put it over here, and then I can calculate it, -3 squared, which gives me 9. So I know what value I inputted for x, and I know what value I get out of here for y. We could say when function of x equals -3, y is 9. Okay? They might also give you something like this, function of x equals 9, and you're trying to figure out what did you put in here to get to 9. They're giving, when they write it this way, they're actually saying y is 9. What is x? X is -3. Okay, a little confusing, I know. You might have to put that back. Okay, here's another one I'm going to put in here. I'm going to put in the square root of k. So this is the square root of k squared. Well, when we square a square root, we get the variable that's underneath it. We actually get the absolute value of that variable. But if you just put down k, it would be okay. But we actually get the absolute value of that because we don't know if k is plus or minus. So when we square a square root, we just simply get the right again. All right, here's another one. Let's take this same one. And what if I put in 1 plus t? Okay, now here I want to figure out what this is. I don't want to leave it like that. I want to expand this out. So I can do it 2 different ways. I could do a FOIL. And I'm going to do first term times the first term, outside, inside, last term times last term. FOIL. And then I can add these together because they're like terms, t squared. So this is one answer to that problem. Another way I can do it is a shortcut way, doing what we call the square double square. Square, double, square. So we're going to square the first term, 1 times 1. We're going to multiply these two terms together. We're going to pretend like we're just multiplying 1 times t. That would be t, 1t, and we're going to double it, so that would be 2t. And we're going to use the same sign we had, and then we're going to square the t. T times t plus t squared. You see, it's a little faster than writing this whole thing out and doing the FOIL. If you're not used to it, you want to practice this because we're going to use this quite often in here. Square, multiply together, double, square, square, double, square. Let's try another one. Let's suppose function of x equals x squared. And now we're going to try to figure out x plus h. So we're going to put x plus h into this problem. This will be x plus h squared. We're replacing this x with x plus h. And then we're going to do a square. Multiply these together, xh, and double that, plus 2xh. You're thinking of x times h and doubling it. And then you're going to square the last term, h squared. We're going to use this quite often in here, this x plus h, at least at the beginning. So x squared plus 2xh plus h squared. This is not x squared plus h squared. X squared plus 2xh plus h squared. Okay, so you kind of get the idea. And I'm going to skip the second example. Some of these examples you're going to have to try on your own. So now we're going to try another one. Here's our function. This is example 5. Because I don't want to keep us here all day. Okay, so here's our function. And we're going to start off by just putting a simple 4. Okay, so that's pretty easy. This would be 4 minus parentheses 4 squared. So that'll be 4 minus 16. So that'll be a negative 12, right? Pretty simple. Okay, now we're going to put in our x plus h. So this is x plus h. We're replacing that with x plus h minus x plus h squared. So we're putting the x plus h into each one of these variables, just like we did before, but it looks a little strange. So this one, we're not doing anything to it, just x plus h minus, but we want to keep the parentheses there, square, multiply and double, square. I'm doing it pretty fast. Square, double, square. Distribute the minus sign, minus x squared, minus 2xh, minus h squared. Are these like terms? Can I combine the x squared with the x? No, they have to be identical. What about this h with the xh? No. This is your answer right here. So, not a very pretty answer, huh? But at least we got an answer. Okay. Let's see, we'll make sure we got it right. Just going to double check it, yeah. Okay, now we're going to take that same problem. It was x minus x squared. And we're going to replace it with, let's see, we want to figure out what f of x plus h minus f of x divided by h is. So first thing we're going to do is put in our f of x plus h. Now we just did that a second ago. We just put in the f of x plus h right here. Remember? And we got x plus h minus x squared minus 2x h minus h squared. So we could do it again if you need the extra practice, but that's what you did. You put in the x plus h. Now, what is this minus f of x? Well, minus f of x means minus And I'm kind of running out of space here. I'm going to squeeze this in the original problem minus this original problem minus x squared. But we need a parentheses. We're taking away this f of x right here is the given problem. So it's saying put in this x plus h like we did over here, then subtract off the original problem, and then when you get through with it, divide the whole mess by h. So let's see what we get. This equals x plus h minus x squared minus 2xh minus h squared minus x plus x squared. Now, if you did it right, and we're going to divide that by h, if you did that correctly, all your x, any term that doesn't have an h with it, will cancel off. This x cancel each other off. Minus x squared plus x squared. So you can kind of verify you're doing it right. This always works. Only h terms should be left. And what we're going to do with these h terms that are left to save a little bit of time, I'm going to factor out the h. So to give me 1 minus, take out the x, 2x minus h over h. And then these h terms are going to cancel because they go into each other one time, and this is my answer. Now, you're very close to figuring out the first derivative of this function. We have another thing we got to do. We got to learn something called limits. And then once we learn limits, you'll be able to take the first derivative of this function. So you can see there's a lot of algebra in calculus. We'll be doing this over quite a few times in this course. Won't that be fun? Okay, we already did some graphing. I don't think we need to go over graphing again. We've already checked that out. But we are going to do another type of graph called a piecewise function. So let me show you this one. And you might remember some of these from algebra. I don't know. Okay, this is what's going to happen if, this could be 4, or if x is a number less than 0, which means when x is negative, y, this is your y value right here. The y value will always be 4. This is your x value, number smaller than 0. Okay? When x is a number between 0, this is a between statement, and 2. It could be equal to, this is not equal exactly, this should be open, this is closed. When it's between 0 and exactly 2, then we're going to use this little formula, y3 minus x squared. And this will give us values for y. It always looks like the 4 should come first. When x is a number bigger than 2, any number bigger than 2, then we're going to use this formula. So we actually have 3 different formulas we're using. We're going to make a table of values. Okay, so it says if x is a number smaller than 0, let's just use a few, -3, y will be 4. If it's -2, y will be 4. If it's -1, y will be 4. And it says also it could be equal to 0. So when it's 0, it could be 4. So what I do on that one is I put a solid dot right here because I want that dot to be solid. In fact, all these dots are going to be solid. We know these are exact answers. But now it says if it's 0 again. So we're going to put 0 in here into this problem. 3 minus 0 squared. 3 minus 0 squared, 0. That would be 3. But so when it's 0, it's going to be 3. But this is going to be open. This is what we're going to refer to as a jump function because it doesn't have an equal sign, so the dot is open. Now, when we put in a 1, 1 is between these numbers. 3 minus 1 squared, that would be 1. That would give me 2. So when I put in a 1, I get a 2, and that would be an exact answer. And when I put in a 2, that also will be an exact answer because it says it's equal to 2. So 3 minus 2, let's put in a 2. 3 minus 2 squared is 4. 3 minus 4 is negative 1. And that's going to be an exact answer. But then it says it has another 2, but this doesn't have an equal sign, so it's not exact. So when we put in a 2, 2 times 2 is 4, minus 6 is negative 2. So when I put in a 2, it's a negative 2, but that's going to be open. When I put a 3 in, well, that is a number less than, so that's going to be an exact answer. I put a 3 in here, I should get a 0. And I do one more. When I put a 4 in here, I get 8 minus 6 is 2. And that's also an exact answer. So now I'm going to graph this. And it looks like I don't have to, most of the numbers are fairly small. This is X, this is Y. Okay. Let's graph this thing. So when X is at negative 3, it's exactly at 4. When X is negative 2, it's exactly at 4. When X is negative 1, it's exactly at 4. And when X is 0, it's exactly at 4. It's also exactly all the numbers in between these. We didn't put down 2.5 and 2 3/4 and all that junk. So this is going like this. Here's our function. It's going straight across. Then all of a sudden, at 0, it says it's also equal to 3. It's also equal to 3. But it says it's an open problem. Open, says Sesame. So we'll put an open dot. At 1, it's at 2. And at 2, it's at negative 1. Okay, just doing those. So it looks like the graph might be a slight curve in it, kind of coming down like that. I don't know. So it's going from this point, not this point, but from this open circle coming on down. Okay. Is this a function? Well, surprisingly, yes, it is. It's called a jump function because this, when you draw a straight line through here, it's only going through one point. This is considered the absence of a point. Okay, so it is a function up to that point. Now let's see what happens at 2 again. Now at 2 again, it says it's an open circle. Again, it's jumping, kind of like Mario Brothers. And at 3, it's solid at 0. And at 4, it's coming up here at 2. Now that looks sort of like a straight line. Maybe my graph's not the best, but it's going like this. And it's going to continue. So we'll draw a line here. This also probably continued. So it was, the function was going this way. It jumped down and kind of caught on the edge of this thing. It's skateboarding, coming down, just catches the edge. And so there's a little distance here. And you can look in your book and you can kind of see. So these are what we call jump functions. I like to do them this way with a table of values. They're kind of fun to do and they drive you crazy. Okay, so that's kind of the main things we covered. We want to talk a little bit more about domain and range. Let's see what the domain of this function would be. Well, the domain means it keeps on going all the way. If we were to project these points down and project these points down, you can see it keeps on going. So we could say it's from negative infinity to positive infinity. But what's the lowest point it goes down to? Well, that's kind of tricky on this one, but I would venture to say it's very close to -2. It's not exactly, but it's close. So that's all we're going to do today. The rate and the height would be all the way up here in 3, 4, 5, 4. Okay, I have a call coming in. I hope you enjoyed this.